So this is our last topic for our National Biochemistry course, and it's on metals. So for this week's lesson, it's going to be a bit of revision from third year metals. We'll look at what the metallic bonding is and the reaction of metals. Now, so we did do this in third year. Okay, so this is revision. The only thing is now that we can do formula, we can take it a step onwards and we can do the reaction with metals and write chemical formula. So first off, we're just going to have a quick review of the different types of bonding we've looked at so far. So we've got covalent bonding, so this could be covalent molecular or covalent network. Electrostatic force of attraction between a shared pair of electrons and the positive nuclei. We've got some examples on this slide. We also look at ionic bonding, where we've got metals will lose electrons and non-metals can gain the electrons to form ions. And it's electrostatic force of attraction between positive and negative ions. And then when we were looking at the bonding, we introduced the metallic bonding. So this is an electrostatic force of attraction between positive ions surrounded by delocalized electrons. That is your SQA definition that you need to remember for metallic bonding. So what happens for metallic bonding is, for example, we've got sodium, it's got one outer electron. So that one outer electron will become delocalized. Now it doesn't just disappear, it becomes delocalized. So it's a sea of moving electrons between the positive ions. Magnesium's got two outer electrons, so its two outer electrons will become delocalized. Now, because these moving delocalized electrons are free to move throughout the structure, this is what makes metallic bonding so good at conducting electricity. Because remember, electricity is the flow of electrons. Delocalized electrons also allow the metals to slide past one another, so it makes metallic bonding malleable and also ductile as well, can be drawn on thin wires. So this just indicates what I said earlier about sodium having one outer electron, so that one electron becomes delocalized. Magnesium has got two outer electrons, aluminium's got three. You can see here the melting point and boiling point is increasing as there's more delocalized electrons, because that's the glue that's holding the bond together. So all these reaction metals, we did cover this in S3, okay? So we'll know the general equations for reaction metals with oxygen, water and acids. What we can take on further is writing equations, because we all know how to write formula. And in third year, put the metals in order of reactivity. We looked at the reactivity. And so we think about group 1, we think about alkali metals. We know that they are very reactive. How they're stored, can we remember? They're stored under oil, because they're so reactive they can react with the oxygen in the air. So if you cut through an alkali metal such as sodium, what you'll see the surface starting to dull in seconds, and it's because the sodium straight away is reacting with the oxygen in the air. And then we've got other metals that's down the bottom of the reactivity series. So metals such as copper might take years and years to react with oxygen, and then we've got our native metals, gold, just doesn't react with oxygen at all. You've seen this experiment in third year. We as teachers, demonstrated it for you guys. So the metals that we used was magnesium, zinc, copper and iron, yeah? Now you've got a test tube, so your metal goes in the centre of the test tube. We'll heat this metal up first to get nice and warm, and at the bottom of the test tube we had potassium permanganate. It's a nice purple colour. So you'll start to apply some general heat to potassium permanganate, or maybe you might have used 2 buntons, one on each of them. As you supplied the heat to the potassium permanganate, what would happen is oxygen would give off. Can you see this formula here? O4, so a plentiful supply of oxygen. So the oxygen would be given off as it passes over the metal, a reaction would happen. Now, as the oxygen passed over the metals would glow brightly as they react. And it was this intensity of the glow that determined how reactive it was and how much energy was released. Now, for balancing the equations, you can see here it's giving you a half oxygen. Okay, so obviously half of that O2 means 1, so it's balancing both sides. 1 magnesium on both sides and 1 oxygen on both sides. Now, if you were to do, excuse my writing, it's not very good with a mouse. Now, if you were to say 2 oxygens on this side, so you put 2 in front of there to turn that into 2 oxygens, and then put a 2 in front of that to turn that into 2 magnesiums, that would also be. So the alkali metals are the most reactive metals. So they're at the top of that reactivity series. And as you go down the group, it gets more reactive. So potassium is more reactive than sodium, sodium is more reactive than lithium. Step 2 and next. Again, as you go down the group, it gets more reactive. So calcium is more reactive than magnesium. Magnesium is more reactive than beryllium. Now, magnesium takes days to react with water, so it's quite unreactive with water. And so your order of reactivity would go potassium, sodium, then lithium, and then lithium is more reactive than calcium, which is more reactive than magnesium. Now, we did say when you put alkali metals into water, you can hear the kind of fizzing of the gas being produced. We tested this gas in the third year, and it burned with a squeaky pop, so it was hydrogen gas that we were producing. And it turns universal indicator a purple colour, so we're making an alkali, and it's a metal hydroxide. That would be a general word equation for metals reacting with water. Metal plus water gives a metal hydroxide, hydrogen. And again, we could go on and we could do chemical formula for these reactions. So the last reaction with metals was with reacting with acids. So likewise, we are able to put the metals in order of reactivity and also write general equations for the reaction of metals with acids. Again, the step one in the National 5 course is to be able to write the formula equation for these reactions. So this is the kind of observations that we might see when you put metals into dilute acid. You can see magnesium's got quite a fast reaction, kind of lots of bubbles being released. Aluminium was quite a fast reaction as well. Aluminium in the lab, sometimes you can't see the reaction as well because it's got an oxide layer. No metals react with oxygen, so sometimes you can form an oxide layer. Copper had no reaction at all, no bubbles, and zinc was kind of medium. Use these observations to put the metals in an order of a decreasing reactivity, so starting with the most reactive metal downwards. So the answers for this slide is on the next slides. Now, if you're watching a video for this, please pause the video and have a go at doing it yourself before you mark the answers. But we want you to write down the word equations and then the chemical equations, balanced chemical equations for these four reactions. Now send off your work to your teacher to have a wee look at to make sure you've completed it. Now just remember the fourth one, copper and sulfuric acid. You can have a wee think about it, go back to your results and have a wee look at the copper reacting.